In this video, we look at a technique that will be useful in section 4.2 and 4.3 from our textbook. It's useful in both the analytic and qualitative descriptions for studying the mass spring damper with sinusoidal forcing terms. Okay, and that method that we're going to be looking at is something called the complexification method. Okay, and essentially, an example usually illustrates it best. An example that we could be looking at here is the differential equation y double dot plus 2y dot plus 2y equal to sine of t. So the forcing function here is sine of t. And let's say that you have also initial conditions x of 0 is x dot of 0 is 0. So you got the initial condition zeroed out. Okay, we've looked at this problem and solved it by using the homogeneous solution, which we know comes about from the eigenvalues. The eigenvalues come out to be -1 plus or minus 1 times I. So the homogeneous solution is either the negative t c1 cosine of t plus c2 sine of t. Okay? And we know that you've also progressed down the route where you can find the particular solution. And one possibility is to take a guess at the solution. It's something times the sine plus something plus a times cosine plus some constant b times sine, and plug into the differential equation and solve. Okay, but the trick with the complexification method is that you need to complexify something, and the complexification happens here by complexifying the forcing function. Okay, which means that what can you put for the complexified force such that when you take the real part of the complexified force, you get the forcing function, which is sine of t. Okay? The reason we want to find this complexified forcing function is because then you could choose the particular solution to be some constant times the complexified force, and the complexified force is going to have exponentials in it. And the exponentials, which we looked at in section 4.1, are what make it easy to find the particular solution. Okay, so what we need to remember is a formula that we developed in class the other day. There was this idea of the key complexification formula. There's a key formula that we developed, and that key formula was that if you had a constant k, e to the I phi, e to the I omega t, okay, that turned into cosine omega t plus phi plus I times the sine omega t plus phi. So that the real part of k e to the I phi e to the I omega t was equal to cosine omega t plus phi. So if we could just get our forcing function, okay, the goal is to get the forcing function in terms of cosine omega t plus phi, which was what we called the amplitude phase form. Okay, so how do we do that? We take the forcing function, which in this case we decided was sine of t. Okay, which means that it is 0 times cosine of t plus 1 times the sine of t. Okay, which means that when you put this into amplitude phase form, you'll get 0 squared plus 1 squared is equal to the cosine of 1 times t, 1 because there's a 1 in front of the sine and cosine in the frequency term, plus phi, the phase angle, where the phase angle is equal to the inverse tangent of negative C2 divided by C1, where C2 is the sine coefficient and 0 is the cosine coefficient. Okay. Which means that the inverse tangent of the undefined value is pi over 2. Okay. Or negative pi over 2 if you wish. Okay. So what we have here is we've complexified our forcing function as the cosine of t minus pi over 2. Okay? Where does this get us? This gets us to the position that we know that, sorry, there was a k in front of here. K. So what we know here is that k is equal to 1, omega is equal to 1, and phi is equal to negative pi over 2. Which means that our forcing function f of t, being sine of t, turns into what we call the complexified forcing function, which just means that it is an exponential, e to the negative I pi over 2, e to the I t. We have something with an exponential function, it just so happens to have complex exponentials. Okay? Notice here that, let's see. I'm sorry, this is e to the I pi over 2. Okay, and you'll remember that e to the I anything is the cosine of anything plus I times the sine of anything. Right. Cosine of negative pi over 2 is 0. The sine of negative pi over 2 is negative 1. So therefore e to the negative I pi over 2 is the same thing as negative I. Okay. E to the IT. Okay, so what we've done is we've completed step 1 of the complexification method, is to turn f of t, the forcing function, into a complexified problem, complexified function, which we have done as negative I e to the IT. Okay. And now we can proceed on to the next step, which is to guess the particular solution. Okay, so we'll continue on here. We can now take a guess at the particular solution is going to be some constant times negative I e to the IT. Okay. And this is what we're going to substitute into our differential equation. And our differential equation was y double dot plus 2y dot plus 2y equal to the forcing function, which was negative I e to the IT, the complexified forcing function. So we need to put this particular solution into the differential equation, which is pretty straightforward to do because they're exponentials, so the derivatives work out pretty easy. Okay, they'll work out to be negative alpha I e to the IT, and then the chain rule says that the derivative of IT is equal to I, so you get negative alpha I squared e to the IT. I squared is negative 1, so you get alpha e to the IT. The second derivative of the particular solution in complexified form is alpha I e to the IT. Okay. Making these substitutions into the differential equation. Okay. Y double dot is alpha I e to the IT. 2 times y dot is, y dot turned out to be alpha e to the it, and then 2 times y particular was 2 times negative alpha I e to the it. And that's supposed to equal to the right-hand side, which was the forcing function in complexified form. Okay. Let's see, now you get to kind of simplify this a little bit. Every term has an e to the it in it. So we'll go ahead and factor the e to the it out. And what's left is alpha I. There's a 2 alpha from the middle term here, and then minus 2 alpha I. Okay, and that's supposed to be equal to minus I e to the it. Okay, so it looks like what we're seeing here. Okay, this simplifies. On the next line, there's minus 2 alpha I, and then alpha I, so it'll be minus alpha I plus 2 alpha. Okay, that has to equal to the coefficient on the other side of minus I. Okay, so what we're going to do, our goal is to solve for alpha. Okay, we just have one parameter alpha to solve for since we've turned it into exponentials, so you can factor out, maybe we should do this in one step at a time. Factor out the alpha, you'll get minus I plus 2 is equal to minus I, so alpha is equal to negative I divided by negative I plus 2. Okay, and we should work with this a little bit to get rid of the complex numbers in the denominator here. So what we're seeing is that if you multiply both sides by the conjugate, okay, then alpha will come out to be 2 plus I times negative I divided by 2 minus I times 2 plus I, which leads you to I squared up here, negative 1 minus 2I, okay, divided by, foiling this out will be 2 times 2 is 4. 4 plus 1 will equal 5. So you will get 1/5 minus 2/5 I. Okay, and there is your coefficient for alpha. And now you know that your particular solution, is 1/5 minus 2/5 times I e. Oh, we got to be careful there. Let's see, substituting right into here. Okay, that we were going to get the minus alpha. We need to multiply this by I e to the it. Okay, which simplified a little bit to, let's see, distributing the negative I, you'll get negative I over 5. Distributing the negative here will be plus I squared is minus 1, so minus 2/5 e to the it. Okay. All right. Okay, if you factor out the minus sign, negative 2/5 plus I over 5 e to the it. Okay, and that's the particular solution. Okay. So what we would have shown here is that your solution to the differential equation, okay, y of t, was supposed to be the homogeneous solution plus the particular solution, but the particular solution has this complex exponential in it, right? And if you go back to thinking about what we did in the beginning, this was actually the complexified particular solution. So if we want to find the real solution to the differential equation, we need to take the real part of our particular complexified solution. We need to take the real part of the negative 2/5 plus I over 5 e to the it. Okay. And if you use Euler's formula, okay, use Euler's formula again, okay, to expand out negative 2/5 plus I over 5 e to the it. Okay, expand it out, and then split it into a real and imaginary part. And what we need is the real part. Okay. You will find that the real part of the complexified forcing function, the complexified particular solution, will give you 1/5 times the sine of t minus 2/5 times the cosine of t, okay, which will lead you to your solution y of t is e to the negative t, the homogeneous, okay, plus the real part of the particular solution that had been complexified. So if you take the real part, you'll get back to a real answer. Okay, 1/5 sine of t, and now we're back into the sines and cosines, which is what we would have had if we had gone the long way around. So there's the general solution to the differential equation, okay, using the idea of complexifying the forcing function. So here's the analytic solution, right? And this idea of the complexifying will show us how to get general solutions to the mass spring damper, which will be the subject of the next video.